Thank you, Professor Adekanian. Excellencies, ladies and gentlemen, with the title of a presentation like this, I better begin and explain why altogether systems thinking is relevant to the nexus of water, soil, and waste. I think you'll agree with me that the set of problems, the set of questions that we have to deal with at this nexus are pretty darn tough. They deal with complexity of different interactions between those kinds of problems, complexity of different kinds of behavior, human behavior, and all kinds of different and difficult to understand environment and society interactions. It's difficult enough to deal with water management. Imagine how difficult it is to try and combine water, soil, and waste management all together. That's why I think systems thinking is relevant, because it's used to. Actually, it promotes the thinking, a systems kind of thinking, rather than focusing on particular elements. It encourages one to think about the whole system rather than its parts, to think about the connections rather than the content, about the patterns that go on in a system. It also, systems thinking has generated over the last 30 years a whole set of mathematical formalities that help us to increase the rigor of how we look at nexus problems, and there's a whole huge toolkit of different ways of dealing with systems analysis, from systems dynamics, from integrated assessment, simulation and modeling, et cetera, et cetera. So there's some opportunity there. The simplest way in which you could take systems thinking and apply it to the nexus approach is simply to use it as a device for visualizing all of the different linkages in a nexus system. Also, systems thinking provides a whole variety of different ways, from causal loop diagrams, which are the simplest way of doing it, to very formal systems dynamics kinds of representation in diagrams. So we can borrow from these different techniques and use it at least to map out the nexus, to try and understand the linkages. But there's so many darn linkages involved with water, soil, and wastes that just mapping out the linkages just gets us part of the way to any kind of solution. What we need to do is to identify the critical linkages. This is also a concept from systems thinking, strong connectedness, it's called often in cybernetics. All it has to do is simply that a connection in a particular system is a critical linkage, a critical connection, if it has a big influence on the overall behavior of the system. Basically, in mathematical terms, it's think of a partial differential equation, dy dx, or if you change x, then it has a big influence on y. It's related to the concept of sensitivity of systems. There's a nice diagram there on the lower right from the literature. This is an example of the connectedness from the standpoint of natural science. This is a map of a part of the Massachusetts coast in the United States, showing the relative interconnectedness of the different aquatic ecosystems along this part of the coast in terms of mass and energy. So why would we identify these critical linkages? With regards to the nexus, we're interested in, first of all, prioritizing factors that have to be studied. Secondly, we could use these critical linkages to build a model that could then be used to look for solutions for integrated water, soil, and waste management. And also, by identifying these critical linkages, like I'll show in the next few minutes, perhaps they give us some insight into where the policy leverage points are. Now, there's a whole bunch of different ways which we can borrow from systems science to identify the critical linkages. First of all, we can sit down with a bunch of stakeholders, like shown there on the right. That's from a study called the Glover-Jordan study. And simply, they're quite smart people most of the time, and they can simply articulate for us, even in a very complex social, environmental, interacting system, what the critical linkages are. You could do it from a qualitative standpoint like that. Or you could use systems dynamics models, which are based on systems dynamics diagrams. Or you could use any number of different modeling techniques that are out there being used for different purposes, as in integrated assessment models or life cycle assessment models. Now, integrated assessment models, most of you know about. They were developed especially in connection with climate change. They combine all kinds of different subsystems from the human standpoint, but also from the natural science standpoint together. I'll just say shortly that they're very useful for spatial temporal analysis of interconnected systems. but they have a relatively limited coverage if you're interested, for example, in the supply chain of energy or the supply chain for the food system. On the other hand, life cycle assessment models are not particularly good if you're interested in spatial or temporal variations, but they were designed especially in order to cover supply chains, looking at an integrated way across industries, for example. Now here's one example in which an integrated assessment model was used, which I would characterize as an application to the nexus of water, soil, and wastes. Here, an image 2 model was used to look at a question having to do with the linkage between the food system and greenhouse gas emissions, also making the connection with climate. Now they looked at, in a conventional way, the linkage of food demand as driven by population and economic growth. But they also took into account an additional linkage, and that's namely the influence of dietary preferences on the per capita consumption of meat and non-meat products around the world, the influence of this per capita demand plus population on food demand, its influence together with other inputs on the amount of cropland used and rangeland used in the world, and then the influence then of this cropland areas and other inputs ultimately on land use related greenhouse gas emissions. So they made this linkage, but the question is still, is this a critical linkage? This is one of many possible linkages. Now with the integrated assessment model, since it's quantitative basis, they could look at different scenarios which they characterize as dietary preferences. There was the reference diet, which I couldn't, looking at the details, I couldn't identify with. Then there was the healthy diet, which I also couldn't identify with, given the fact that I like Würstel too much. They characterized these dietary preferences, made the linkages shown in this integrated assessment model, and could quantify for a particular set of conditions that in 2050, that the land use, the resultant land use emissions would be a full 1/3 less for the so-called healthy diet preferences as the reference diet. The point being that integrated assessment models and other similar models can be used to articulate the linkages at the nexus of water, soil, and waste, and furthermore can be used to quantify these linkages to assert whether these are critical linkages or not. Now, for various assessments having to do with the nexus, certainly often we'll need spatial assessments. As in the case I just showed you, the estimation of land use emissions has a lot to do with local conditions. It has to do with the amount of fertilizer applied. It has to do with the local climate conditions, etc. So it's obvious that in order to make that kind of linkage in a nexus problem, you'll need some kind of spatial assessment capabilities, and that's where integrated assessment models are very useful. On the other hand, if you're interested in another nexus type of problem, for example, the impact of bioenergy in general, bioenergy production on the environment, on water quality, for example, then you're interested not particularly on the spatial resolution or temporal resolution, but you're interested in looking at the impact of the energy crops, for example, and their impact on water pollution, and, for example, the impact of bioenergy conversion facilities, which will have an entirely different impact on water quality as the impact of energy crop growing. So in that case, you're interested then in the cutting across, you're interested in the various aspects of the supply chain. So the point I just wanted to make is that, in my view, the nexus approach will require a wide variety of different kinds of models, and in some cases will also and should also stimulate the combining of different modeling approaches we have now. And one task that I think we need to get to as quickly as possible is to create to do a systematic overview of the system tools that are out there that we can apply to nexus problems. Now, what I'd like to now is make a bridge between this idea of critical linkages and other systems ideas and how it can influence our considerations of management at the nexus. And what I'd like to talk about is an issue very important when you talk about the nexus of water, soil, and waste, or any other nexus, food, energy, and water, for example. And that is namely resource efficiency. And also a particular issue now hotly discussed about resource efficiency, and that's namely the rebound effect, which just very briefly put, simply means whether the question of whether efficiency improvements achieve their intended targets, their intended goals. Now, this has been studied for already 2 decades in the energy area, and so our research colleagues tell us that, in fact, that there is a so-called rebound effect in the building sector and also in the vehicle sector of around 10 to 40%. What does that mean? That means that if a set of conservation measures are intended to reduce energy use relative to a baseline by 50%, in reality, they'll only achieve a reduction of 40% or maybe 30%. When you've finally gotten rid of your gas-guzzling car and bought a nice energy-efficient Golf, and you go out there and say, hey, I'm saving a lot of money on gasoline, so I'm going to take at least 3 more trips out to the countryside this month than I would normally, then you are contributing to the rebound effect. And you, by the way, can personally fight it, that if you do get in that situation, simply don't take more trips. But in any event, this issue of the rebound effect is slowly making its way also into an important area relevant to the nexus of water, soil, and waste, namely into the issue of irrigation water efficiency. And the question is whether efforts to improve the efficiency of irrigation water projects are achieving their end result, which from the systems perspective you could characterize as a whole systems goal of maximizing the ecosystem services that we are trying to derive from water and from land in terms of food production, while minimizing waste production. So here's a set of case studies, one from the Rio Grande in Mexico and the United States, and one from the Ebro River Basin in Spain, that come to amazingly similar conclusions, which I'm going to sketch out for you. In these projects, or in these case studies, they studied the actual transformation that occurred in these districts, in which public funds were used, in the case of the Rio Grande, to switch from surface irrigation to drip irrigation, moving from a roughly 50% field efficiency to drip irrigation can achieve 90% or higher field efficiencies. And then in the case of the Ebro, shifting using public funds from surface irrigation of around 50% efficiency to pivot irrigation, which you can get about 75% or 80% field efficiency from it. So under the status quo, the irrigation projects in these river basins were, and still are, having high irrigation water demands, which are leading to an overall sense of water scarcity in these basins. Responding to this sense of water scarcity, or actual water scarcity, the governments have subsidized the improvement of irrigation efficiency in these irrigation projects, making the efficiency improvements that I noted, going from surface to drip in one case and surface to pivot. This, in fact, did in fact lower the amount of irrigated demand. In the case of the Rio Grande, under the highest level of subsidies, the estimate is that the amount of irrigation demand relative to the baseline decreased by about 10%. Now, the catch is, because of the high efficiency of these other measures, it also means that plants transpire this water very efficiently. And there's a net increase, much higher evapotranspiration occurring on the cropland, at least relative to the amount of runoff, which will and did decrease the amount of return flows. How much? In the case of Rio Grande, they decreased irrigation demand by 10% and decreased return flows by 50%, which led to a substantial decrease in water availability downstream, which the consensus is, in both of these river basins, that there's been actually a net decrease in water availability. A lot of angry downstream irrigation users, a lot of angry downstream countries from irrigation users, for example. So how can we respond then to this rebound effect? Well, the same authors of these case studies suggest that the main way of responding would be to take a whole basin approach, and that is to restrict either the acreage of irrigated crops or restrict the total water uses for irrigation in the river basin in order to achieve more basin-wide water availability goals. Therefore, this would lead to a reduction in the irrigated area, and therefore the higher evaporation coming from the efficiency improvements would be compensated by the reduced irrigated area. More transpiration over a smaller area, which would lead to an increase or no change in the water availability downstream coupled with the efficiency improvements, should lead to a net increase then, which would be the whole basin goal, in water availability downstream. Interestingly enough, in Kansas, there was another case study, which in this case, the irrigated croplands are having a major impact on the Midwest aquifer. In fact, there's some parts of Kansas where, since the 1970s, because of irrigation, the water table has dropped by more than 40 meters, if you can imagine that, 40-meter drop in the water table. Responding to this, to the water scarcity in the groundwater resources in the Midwest, the state governments here subsidized the improvement of the efficiency of the pivot irrigation to a new form of pivot irrigation using a new kind of nozzle which greatly improved the efficiency of that kind of irrigation. Now, what the upshot of this, in this particular case study in Kansas, was that the farmers realized that, hey, now I have more water for the same investment, a much lower marginal cost, or I can use the same quantity of water and invest it elsewhere. And they're not stupid people, and that's, in fact, exactly what they did. As a result of the efficiency improvements, they partly shifted to more water-intensive crops, like soybeans, for example. And, as was found, they ended up using irrigation more frequently than the baseline and used it on marginal lands, which they weren't using previously, which, of course, set a nice negative feedback, a positive feedback rather to irrigation water use, which in fact did increase in these case studies, which did increase groundwater withdrawals and led to increased depletion of groundwater. It's a fascinating case study. Again, here, the idea of solving this is similar to in the previous case studies, and that is the need for a basin-wide, systems-wide approach rather than a narrow looking perspective, where you would restrict water allowances either based on a decrease in water rights or maybe taxation of water, which in principle should discourage the shift to water-intensive crops, should discourage the more frequent and intensive use of irrigation, and should lead to a negative feedback in irrigation water demand, and ultimately a decrease in the rate of depletion of groundwater resources. So, what are the lessons to be learned? I don't know what lessons you can learn or what they've learned, but what I've learned from looking at these case studies, viewed from the system standpoint, I see the rebound effect as a failure to achieve a systems goal, which I think in these cases would be maximizing the ecosystem services we want to derive from water, we want to derive from soil and land in these river basins and in these groundwater basins, and minimize the waste at the same time. I think the rebound effect comes from omitting, neglecting critical linkages in the system, especially those linkages that have to do with human behavior, like the farmers reacting to a cheaper marginal cost of water. I think these case studies also showed us that we can find solutions if we look at the larger system and if we include critical linkages. Also, the case studies showed us that solutions do arise if we look at the whole resource, if the whole resource is taken into account in our decision-making rather than just the immediate aims of efficiency improvement. In any event, over the last 18 minutes, I was only able to touch on a few of what I see being the aspects of systems thinking that can really help out in us dealing with the tough challenges, dealing with nexus problems of water, soil, and wastes. I think there's the elements, at least, are there for a general approach to using systems thinking for nexus problems. There's the aspect of mapping the nexus system and articulating the linkages through a mapping exercise, and through this exercise also clarifying what the whole system goals are. There's using models that are already available, or perhaps combining them or developing new models in order to quantify the linkages. And based on this quantification of linkages or otherwise, identifying the critical linkages that will influence the behavior of the system, and using this insight from critical linkages as insight for policy leverage points that may suggest to us new ways, new policies for controlling problems at the nexus. So I think in general, you'll agree with me that problems at the nexus of water, soil, and waste are particularly tough problems. And I think that systems thinking can help us organize the way we think about these problems a bit, maybe add some rigor in ordering these problems, and help us not only to understand the problems better, but to find also good nexus solutions. Thank you very much.
Thank you very much, Professor Alcamo. Very interesting presentation. I learned myself that this Nexus approach is mainly or more a mindset rather than some mechanical mechanism. So, floor is open for a quick question, please. Yes, if you come to mic and introduce yourself.
My name is Max Maurer from the Swiss Federal Institute of Technology. Thank you very much for the talk. It was very interesting. There's one. So I'm a scientist as well. We deal extensively with modeling, and you touched on the modeling and the results it can produce on that. We find it extremely difficult to communicate these results, and I would like to see what's your perspective on that. So just to give you an example, now we work in the water area. There we produce results that sound like we achieve the goal 85% of the time with a probability of 65%. That's for 2025, but for 2035 we have this result. This is for scenario 1. So we also have scenario 2, and we have a different impact factor, so we have a different performance indicator that also have different results. How do you communicate stuff like that with a stakeholder and make decisions? What's your take on that? What's your experience on that?
Thank you.
How much time do you have?
Not as quick as the question.
I think that the whole issue of the science policy interface, especially as it has to do with the nexus, is an absolutely critical issue. And I think that maybe we should spend a whole session sometime at one of the conferences talking about the connections. One immediate practical answer to your question is hold a workshop. Hold a workshop between 5 scientists and 5 policymakers, and give yourself 2 days to clear up all the misunderstandings that you're going to have in the first day. That's just one simple way, and I can give you another dozen ways of doing it, but don't give up. That's all I can say. Because as it turns out, the research that, I'm now back in science, if you're going to do that kind of science, you have to think about it. It's not pure science. It's not basic science. You're not contributing to quantum physics or anything. It's justified by the policy context. So we as scientists have the responsibility to convey this. We don't have a choice. So stick with it.
Thank you very much. Just one more, if very quick.
The
lady, please.
Oh, sorry.
Okay, sacrificed.
Yeah, thank you very much. I'm Michael Herman with the UN Population Fund, oder Michael Hermann auf Deutsch. My intervention is really inspired by a number of presentations, including Mr. Steinhagen's and Marais and your own. If I look at this triangle of the key resources, water, soil, waste, or the major sectors, food, water, energy, in fact, I do feel that this takes place in a broader context. And that's the human context. That's a critical link that might have been left out of this discussion. Why are we concerned about this? We are concerned because this triangle affects us humans. It increases our vulnerabilities, but also because our behavior is really what makes this triangle sustainable or unsustainable. And of course, it's not only the number of people that we are on the planet that matters. It's also the living standards that we have and aspire to, the way we distribute what we have, and the way we produce what we need or want. So I hope that in this discussion, in these coming days, we also will think a little bit about the human dimension of this nexus. And keep in mind that, in fact, as Mr. Steinhagen said, it's not a mere engineering problem. It's a question also of ethics. It's a question of human rights. One position paper wrote that we need serious population controls. I don't know what that means. but I would encourage all of us to have a rights-based discourse on these population matters. Thank you.
Thank you. Any comments? Thank you so much. Thank you very much, Professor Alcamo. I think